Okay, today we're going to be talking about the rules for how to evaluate a derivative the shortcut way. And we have already looked at the standard definition of a derivative, and that certainly takes a long, tedious process. Actually requires a long, tedious process, but today we're going to look at shorter ways to take a derivative. And so the first rule we're going to learn is, what is the derivative of a constant function? Well, let's say we have the function, let's just say it is y equals 6. And so if we go ahead and graph that, that's going to just be a horizontal line. And so if we know that the word derivative is synonymous for slope, then now we can say that the derivative or the slope of any constant is going to be 0 because the slope of a horizontal line is 0. All right, now we're going to learn the power rule. And the power rule is a pretty simple way of evaluating the derivative. It works whenever you have the base of a function to be just a single letter x and the exponent is a number. It doesn't have to be an integer, it could be any number. And all you do is simply take the exponent and you multiply that exponent times whatever coefficient is in front of the x. In this case, it's 1. And then you subtract 1 from the power. So f prime of x is going to be 3. Leave the x there and subtract 1 from the power, 3x squared. And that essentially is all the power rule involves. And so you can see that this is a lot easier than the standard definition of a derivative. Here we have y equals x to the 1/2 power. So we always want to write the radicals with a 1/2 power. If it's square root, if it's cube root, write it as 1/3 and so on and so forth. And so now we're going to use the power rule. So we're going to take this 1/2 and we are going to multiply it in front. So it's going to be 1/2 x, subtract 1 from the power, so negative 1/2. Then we never want to leave two things in our answer. We don't want to leave a negative exponent and we don't want to leave a fractional exponent. So we're going to move this x to the negative 1/2 down to the bottom and make it a positive 1/2. And then we're going to write it as 1 over 2 square root of x. And that is going to be the answer that we want here. So now let's move on to the third example here. We're going to rewrite this as t to the negative 4th. And that's gt, g of t. So g prime of t by power rule is going to be negative 4. Multiply that in front. T, and subtract 1 from the power. So that's not going to give you negative 3, but negative 5. And then we're going to rewrite our final answer as negative 4 over t to the 5th. And essentially, that's all that is involved with the power rule. Okay, now we're going to use the power rule to evaluate a sum of terms or a difference of terms. And essentially, all you do is just take the derivative of each term separately. So f prime, maybe we'll separate this here, f prime of x is simply going to be 3 times 4, which is 12x, subtract 1 from the power. 2 times 5, negative 5 is negative 10x, subtract 1 from that power. Now here you do not need to use the power rule. Remember, the derivative is the same as the slope. So therefore, the slope of 7x is simply 7. So that's just going to be 7. And then the slope of any constant is going to be 0, as we discussed before. So there is your derivative. Now, this next example, a lot of students may think that they need to use the quotient rule, which we're going to learn in just a few minutes. But you actually don't need to use the quotient rule. One of the rules that you want to always keep in mind in calculus is, if at all possible, always do algebra before you do calculus. Because algebra will always make your calculus easier. So what you want to do here is you want to recognize that you can divide this x into all three parts of the numerator. And when you do that, you will be rewriting y to say 5x to the 4th minus 3x cubed plus 4 divided by x. And I'm going to rewrite this last one to be 4 times x to the negative 1. So let me erase that and write that as 4x to the negative 1. So now our y prime just becomes 4 times 5 is 20x to the third minus 9x squared. And the negative 1 times 4 is negative 4x. Subtract 1 from that power is negative 2. So our final answer is 20x cubed minus 9x squared minus 4 divided by x squared. And essentially that's all there is to the sum and difference rule. Okay, example 3. Determine the point or points at which the given function has a horizontal tangent line. Okay, so let's see if we can interpret what they're asking here. A horizontal tangent line would be a tangent line you draw to the curve that's horizontal. So that would mean that the slope of this line would be 0. So essentially, if we just can kind of visualize what this function looks like, it's a cubing function. And unless it goes through the origin, a lot of cubing functions are essentially going to look something like this. All right, so they're going to have, we'll call this a maximum, has some sort of maximum point and some sort of minimum point. So if we were to draw a tangent to this curve, we would see that that tangent line would have 2 points on this curve where the slope is 0. And we'll learn that later. The slope is 0 at a maximum or minimum point. So essentially, that's what this question is asking, is where is the maximum and minimum points on this graph? So we're going to rewrite, we're actually going to take the derivative. F prime of x is 3x squared minus 12. And then, because we know the derivative is another word for slope, we're going to set our slope equal to 0 to determine what x values on this curve give us a slope of 0. So when we move the 12 over, divide by 3, and take the square root, we get plus or minus 2. And so you can plug those values back in, and you can get the y values as well, but the x values are plus and minus 2. Okay, here we have what's called the product rule. And the product rule essentially says that if you have two functions that are being multiplied together, that you take the first function, f of x, times the derivative of the second function, plus the second function times the derivative of the first function. So let's see how this works in this particular problem. We have, let's just write f prime of x is equal to the first function, x squared plus 1. So you just copy that straight down, times the derivative of the second function. Well, that's just going to be 3x squared, plus the second function, x cubed plus 3, times the derivative of the first function, which is just 2x. Now when we distribute this in here, we will get 3x to the fourth plus 3x squared plus 2x to the fourth plus 6x. And so we end up with a final answer, f prime of x, to be 5x to the fourth plus 3x squared plus 6x. Now, that is only one way of doing this problem. And notice that we did this problem by doing calculus first, and then we did a little bit of algebra to group up our like terms. Now I'm going to do it the way I would probably do this problem, was without using the product rule, and that would be to use algebra first and then calculus. So algebra would say FOIL this together and rewrite f of x as x to the fifth plus 3x squared plus x cubed plus 3. Then when we do the calculus portion, we don't even need the product rule. We can use the power rule. So 5x to the fourth plus 6x plus 3x squared, and then the derivative of any constant is 0. So using the algebra first instead of calculus first can sometimes make our calculus easier. Okay, now we're going to learn the quotient rule. And the quotient rule is similar to the product rule, except it's a little more complicated. You take the lower function, g of x, times the upper function, f prime of x, derivative, minus the upper function, f of x, times g prime of x, which is the lower function's derivative, divided by the lower function squared. Sometimes teachers will give you a little easy way to remember this, which is low d high minus high d low over low squared. Low function times the derivative of the high function minus the high function, let me write that in there, times the derivative of the low function. So let's see if we can apply that. The low function is x squared plus 1 times the derivative of the high function, which is 5, minus the high function times the derivative of the low function, which is 2x. And all of this is divided by the low function squared. Now, please do not FOIL the low function out ever. You'll always want to keep it in this form. So whenever we group our like terms together by distributing the 5 and moving forward there, you get 5 x squared. Actually, you end up getting negative 5x squared. And then you will end up getting, let's see, positive 4x, and then you'll get a positive 5. And all of that is divided by x squared plus 1, all squared. And this is y prime. Okay, so now we're going to do letter B. And always remember, algebra first before calculus. So you must always ask yourself the question, do I have to use the quotient rule here? Or can I recognize something that I did earlier in class? I can split this up into two fractions, and I can do a little bit of algebra before calculus. So I'm going to split this up into x squared over x to the 1/4 plus 2 over x to the 1/4. Then I'm going to subtract my exponents and get x to the 7/4. And then I'm going to move this up to the top and make it 2x to the negative 1/4. Now all I've done was use a little bit of algebra to rewrite this equation, and now all I have to do is use the power rule instead of the quotient rule. So let's go ahead and do that. F prime of x is equal to 7/4 x to the 3/4, which is what you get when you subtract 1 from this power, and then minus 1/2 x to the negative 5 over 4. Now let's rewrite this without negative exponents and without fractional exponents. So your final answer should be f prime of x is equal to 7, and then it's the inside power divided by the outside power. So the 4th root of x cubed, and then we have here minus 1 over 2 times the 4th root of x to the 5th. Example 6 says to find the first 4 derivatives of this function. So we'll write the first one as y prime, and that will be 3x squared minus 10x. And the derivative of 2 is 0. Second derivative, same way, 2 times 3 is 6. Drop the power down. The derivative of any linear function is its slope, so negative 10. And then the third derivative is going to be the derivative. This is a linear function, so we'll say 6. And then the fourth derivative, we just use a little 4 up there. And we'll just put parentheses around it so that we don't think it's y raised to the 4th. And then the derivative of any constant is 0. Okay, number 7 is a complex problem. It says find the value of k so that the function x squared plus kx will be tangent to the line y equals 2x minus 9. Perhaps a visual representation of this would be helpful. Let's say we have some parabola, and let's say it looks like this. And then we have some other line, y equals 2x minus 9, that let's say, is tangent to the curve. So it looks like this. The question that we want to find, or question we want to ask is, what value of k will create this situation where this line is tangent to this particular parabola? So notice that two things are true here. The first is that the tangent line has to touch the curve. That means they have to be equal to each other at a certain point. So the first thing is true, is that the functions must equal each other. In order for there to be a tangent line, they have to be equal to each other. Now the second thing is they can't just be equal to each other, but the slope of this red line has to be equal to the derivative of the yellow curve at this point. So the derivatives have to be equal to each other. So the slope has to equal slope of the line has to equal the derivative of the function of the curve. Let's just write it that way. So now we know two things that we need to do. So the first thing we need to do is we need to set these two equations equal to each other. So x squared plus kx must equal 2x minus 9. Second equation we'll get by setting the slopes equal to each other. So we'll take this derivative here, which is going to be, so we'll call this equation 1. Equation 2, maybe we'll put equation 2 in yellow. So equation 2 is going to be 2x plus k, which is the derivative of the curve, and that must equal the derivative of this function, or the slope of this line, which is 2. Now, when I solve this for k, I'm going to get 2 minus 2x. And I notice that I've got two variables over here, x and k. That's not good, but we can take this, we can plug it in here, and now we'll only have one variable. So let's do that. X squared plus k, which I'm going to write as 2 minus 2x, times this x right there, is equal to 2x minus 9. Then when I distribute this x, I get x squared plus 2x minus 2x squared equals 2x minus 9. Then I recognize that this 2x and that 2x are going to cancel out. And when I group my like terms, I get negative x squared equals negative 9. So x equals plus or minus 3. When I take both of those values and plug them in here, I get a k value of negative 4 and a k value of 8. Now you say, why do I get two answers? Well, because if I extend this tangent line, let's actually draw it down a little bit more, then that will prove to us that there is actually another parabola down here that also has the 2x minus 9 tangent to the curve, and two different x values and two different values of k. Example 9 says we need to find a and b to make this piecewise function differentiable everywhere. Now, if we just look at this first part, ax squared plus 1, that's a parabola. So we know that's differentiable everywhere. And it's bx minus 3, that's a linear function. That is also differentiable everywhere. But the question becomes, what is going to happen when these two functions meet? Is it going to create a sharp corner, or is it going to create a nice, smooth transition between these two functions? So we need to create a situation for a and b such that these two functions will create a function that will be differentiable everywhere. So the first thing that has to be true is if this function is going to be differentiable everywhere, it must first be continuous everywhere. So we have to make sure that these two functions have the same y value when x is plugged into them. So we take our 2, plug it in for x, and we get 4a plus 1. That must equal, when you plug in 2 for x, that must equal 2b minus 3. So the equations must equal each other. And that is going to make it continuous everywhere. Now, second thing is that the derivatives must equal each other. And that makes it differentiable everywhere. Meaning the slope from the left has to equal the slope from the right. So 2ax must equal b when x is 2. So 4a must equal b. So now we can just replace 4a with b. So b plus 1 equals 2b minus 3. Move the b over, move the 3 over to the other side, and we get b equals 4. And then if b is 4, then a must be 1. So the process here is you set the equations equal to each other to make sure it's continuous. Then you set the derivatives equal to each other to make sure there's no sharp corners or cusps at the point where the two functions meet. Okay, final problem on these notes is example 10. Find the equation of the parabola ax squared plus bx plus c that passes through the point 0, 1 and is tangent to the line y equals x minus 1 at 1, 0. All right, so let's just see what this is saying. We have three variables, a, b, and c. So that means we need to have three equations, if you will. The first one is that it has to pass through the point 0, 1, meaning when x is 0, y must be 1. So if we plug in 0 for this x and that x, that wipes these terms away. We plug in a 1 for our y. We quickly realize that c equals 1. So one of our letters is already accounted for. Now, in order for this parabola to be tangent to this line, once again, two things must be true. First of all, the parabola must go through this point, meaning this point's got to be on the parabola itself, and the derivative of this parabola must equal the slope of this line. So it's the same as number 7. So let's go ahead and plug in 1 in for our x's and 0 for our y, because you can't have a point of tangency that is not on the curve. So 0 is my y, 1 is my x, and we've already got c to be 1. And so we know that we have at least one equation with a's and b's. Now let's take the derivative of this parabola. 2ax plus b. And that has to equal the slope of this line, which is 1, when x is 1. So now we take that 1 and plug it in there. So we have 2a plus b equals 1. So b can be written as 1 minus 2a. So now we take that, plug it right back there. So let's see what we get. A plus b, but b is 1 minus 2a, plus this 1 equals 0. So we get negative a plus 2 equals 0. So a equals 2. There's our second letter. And then we take this a equals 2, plug it right here, and we end up getting b to be equal to negative 3. So once again, you have to have, if there's a line that's tangent to the curve derivative and the slope of the line must be equal at that point of tangency. So that's why we had to plug in the 1 in for our x.